Okay, so we're going to take a look at some difficult, or at least relatively difficult, one-dimensional kinematics problems. Now, one of the things to keep in mind is, by my consideration, especially using the kinematic equations as we do in my classes, I don't really consider there to be a whole lot of one-dimensional kinematics problems that can get very challenging unless you have complex motion where several different things are happening. Something changes its motion partway through, for instance, where a car might be accelerating, then hit a maximum speed, and then stay going at that same speed for the rest of the period. That's one thing that we could take a look at. Or another way to make one-dimensional kinematics problems more complex without having different sections of motion is by having more than one object. So we're going to take a look at a real-life type question. Let's say that we've got some runners, and we've got runner A, who starts a race back over here, runner A, and we'll say that runner A runs with a constant speed, constant velocity. Let's go with maybe 8 meters per second. Great. And then we've got runner B, that's running over here, B, and then let's say that runner B runs with a constant velocity of, I don't know, let's go 11 meters per second. Now in this case, I should point out, if I want to call it a velocity, the way that I've set this up, one of them needs to be negative because they're going the opposite direction. So we'll go ahead and make B negative because they're going to the left. But they'd be running with a speed of 8 meters per second and 11 meters per second, respectively. So that's their speed. But when we take into account their direction, one of them will be negative, and we do need to keep track of that. Now let's say that these two people were setting up for a long distance run. Let's say that they are, I don't know, maybe 10 kilometers apart. So this would be a decent enough example of it, but not drawn to scale. Here's what I might ask as a more complex question. Let's say that your job is to be a photographer and you want to catch the point where they are going to run into each other, and you need to set up a camera there to catch the whole thing. Now the problem is, you don't necessarily know where to put the camera. So do you have to run with your camera alongside with this person, and then when you start seeing the other person get close up, you run quickly ahead and try and set things up in a flash? Probably going to be pretty difficult. So let's see if we can go through and make an estimate on this. Now this is kind of a contrived one with two racers, but you might have something where you had people who were doing a cross-country meetup, where you would have an idea of where you could set up for them to pass one another. So I think originally I was going to do this with hot air balloons going the distance of the country, but it's actually the same thing. All right, so here's what we want to do. We want to find at what spot we need to set up our camera for these two runners to meet. Now we're going to say that they both start running at the same time, and they start running 10 kilometers apart. Now, one of the things that makes this complex is we've got several things that we don't know. So if we were going to look at, we've got two objects, so let's set up our kinematic variables for each of them. I'm going to have delta x, the displacement of runner A, so I could put delta x A. I could do v final A, v initial A, acceleration of A, and time of A. Great. So I've got all that set up. And then I can do the same thing with person B over here. Delta xb, the displacement of runner B, final velocity of B, initial velocity of B, acceleration of B, and time of B. Okay, we don't have a whole lot of information, but we've got some. I did say that runner A is running with a constant velocity of 8 meters per second. So that's our initial velocity. And because it's a constant value, it's actually our final velocity as well. We could point out that since runner A does not speed up or slow down in one-dimensional motion, they're running with a constant speed, we also know that their acceleration is 0 meters per second squared. So we can fill in some good information. The downside is, for what we're looking for, we don't know how far runner A is going to run, and we don't know how long it's going to take for runner A to run into runner B. We can fill similarly in over here, negative 11 meters per second, negative 11 meters per second, and then finally 0 meters per second squared. Neither of them are speeding up or slowing down. Pardon me, we're saying that they run with a constant speed or velocity of their various values. Now, runner B, we do need to keep in mind, is negative 11 meters per second. Great. All right, so now what do we do? What are we looking for? There's all sorts of stuff that we could try and go for, but here's where it gets more complex. We have to think about what's going on. And this is one of the things that is actually a lot more classically physics because we're asking a real-life problem. A bunch of the other things that we've looked at are basically just slightly more complex word problems from a math textbook. But here is where we're setting something up that is actually about finding a real answer. Trying to know where you'll put your camera so you can have plenty of time to set up to get the perfect shot. You might do this for special effects or something else. Like this could be an actual thing that you would need to do in a career. So let's see how we can work with it. If you are not already doing this, I heavily recommend that you draw out problems, especially if it's a problem like this, because it helps you set up a number of things. In fact, I've been doing this for, at this point, over a decade, and even I have trouble setting some of these things up without seeing them. Now, what we need are some relationships. We've got 3 pieces of information, but since our accelerations are 0 for both of them, we can't actually find a whole lot. You're welcome to plug these into some equations, and you're going to find that you have some dead ends because you'll have to divide by a 0 at best, and that's just not going to work out. We're not going to be able to find either our time or delta x with just the information we have here, so we have to set up some relationships. What's governing this problem is the fact that we have 2 different objects that are interacting. It doesn't really matter what A is doing by itself or B is doing by itself without looking at how they interact with one another, because we're looking for a point where they both meet a set of conditions. Now, we're going to say that time starts at time equals 0, and we're looking for some time later where they meet. So I'm going to call that, let's see, so we'll say that time, our initial time, is equal to 0 seconds. So we start the stopwatches as they begin running 10 kilometers apart. And that we are looking for some time later, t, where they meet. And that time will be the same for both of them. So time A will be equal to time B will be equal to t, where they meet. In other words, if they meet up 2 hours later, then this person A has been running for 2 hours. This person B, has also been running for 2 hours. Now, we may not know what that time is right now, but we can say that based on our problem, those are the same. Now, that might not be the case in the future. In the future, you might have a slightly different problem in which runner A starts running at 10 o'clock and runner B starts running at 10:15. And so you might have a time difference where it wouldn't be TA equals TV. You might have TA plus 15 minutes, whatever that is in seconds, equals TB. And so things to think about where we could change all of this out, but we need some relationships. Now, that relates our times, which are good, but I still don't know any of the numbers to fill in there. I just know that they're equal to each other. So I need to come up with another relationship as well, and here we need to look at our displacements. And here's where drawing it out becomes very useful. Now, I know that this is some location x that I'm looking for. I'm going to call this an x, a position of 0 meters. And then over here, we're going to say that this is a position of 10,000 meters, 10 kilometers. So I'm setting up a coordinate system with 0 at where person A is, and 10,000 meters, 10 kilometers, is where B is at. And what I'm looking for is position x. So if x is 100 meters, I know to go 100 meters from here over to here and set up my camera. So that's going to help out. Now, that gives me a reference, a way of working with this, but it doesn't actually finish solving all of my problem. Here's the other thing that I'm going to need. So I don't know where x is, but wherever x is, I know eventually runner A will have run this displacement, delta xa. And that could be here, it could be over here. I've drawn it just kind of randomly in the middle-ish. And I know that delta xb is this. This is how far that runner B has gone. And no matter if I move the camera, oops, edit undo. There we go. No matter if I move the camera over here, well then this would get shorter, but what would happen to this? It would have to get longer, because both of them have to have gone a given displacement to meet up. And this is where having it drawn out helps out a lot. So I can do delta XA plus delta XB equals 10,000 meters. This is something that is specific to our problem. No matter where this meetup point is, I know that with this setup, delta XA and delta XB together must be the total length that they start apart, 10,000 meters. Now, one of the things that I want to bring up on this is you may have to be careful with your negatives in this. Remember, delta XB is the displacement, but it will be to the left. So for this relationship, what we really want is the absolute value, the magnitude of our two displacements. Because technically delta XA is going to be a positive value, and delta XB is going to be a negative value because they're going to the left. Great. But now I've got some stuff set up here. Okay, okay. Well, I could do the following. I could then put one of these over. Let's see. Delta XA equals 10,000 meters minus the magnitude of delta XB. So what I've done is I've subtracted delta XB over to the other side. I don't know what delta XB is, the displacement of runner B, but it could be, I don't know, 8 kilometers. And if it's 8 kilometers, that means that 10 kilometers minus 8 kilometers would leave us 2 kilometers. That's how far runner A must have gone. Okay, now I can start working with some of these things. So what I'm going to do is I'm going to set up an equation here, and I'm going to say that our time is going to be equal to time t, which is whenever they meet. And I don't know when that is, but let's see what we can find out. I'm going to solve for delta XA, but I'm going to have to solve it in terms of other things. Well, I've got all the information that I could want, although I don't actually know what t is. It's a variable, it's a number, I just don't know it yet. So I'm going to leave it as t, where t is the time that they meet up, and that's how I'm going to find my delta XA, which is how far runner A will have gone when they meet up. So I can use just about any of the equations that I want. Let's go with the most common, equation number 2 on our equation sheet, which would be delta XA equals V naught A, our initial velocity, times our time, plus 1/2 acceleration of A times t squared. I'll fill this in. I don't know delta XA, so I'm just going to leave that. V naught A, we said, was 8 meters per second, I believe. Let me double check my numbers. 8 meters per second. Great, positive. Times t, in this case I could write my green t, that's the time that they meet up, plus 1/2 0 meters per second squared, because it's a constant velocity, times t squared. Well, this last term doesn't actually matter much because this is 0, so it doesn't matter what t is. When I multiply it by 0, this whole thing disappears into a puff of nothingness, and I get the following. That delta XA is equal to 8 meters per second times t. Okay. Now, I don't know delta XA, and I also don't know t, so you may be wondering, okay, how is that helping me? Well, I can now replace this, my delta XA, with 8 meters per second times my unknown time. Let's take a look at the delta XB. Okay, we had pretty good luck finding delta XA. I now know, for whatever reason, that it is 8 meters per second times t, where t is the time that the runners meet up. All right? Let's do the same thing over there for B. Well, let's see what B comes up with. I would use the same equation. I'd have delta XB is equal to our initial velocity in B, that's negative 11 meters per second, negative because it's going backwards, times t, plus 1/2 our acceleration, 0 meters per second squared, t squared. Once again, since there is no acceleration, our acceleration is 0, that last term disappears, and we find that whatever the displacement of runner B is equal to, well, negative 11 meters per second times time. Okay, well, I can fill that in. Negative 11 meters per second. Oh, let me do this in black so that we draw attention to the fact that it's not an actual number. It's something that we need to know the time on. Okay, that's fine. All right. Now that we've got that, you may be thinking, well, how's this getting us closer? Well, we're setting up relationships. We don't know how long it's going to take, but we do know that the displacement of runner A is equal to the velocity of A times the time, because there's no acceleration. Same thing with B. So what we need is to solve for the time where delta XA and delta XB add together to be 10 kilometers. Now that's the way that I've ended up doing this here. You could have also tried to put t in terms of some delta x, A or B, but I like working with the time side of this. So we now know that the magnitude of delta XA is equal to 10,000 meters minus the magnitude of delta XB. And here's where the magnitude becomes important, because we need both of these to be positive numbers. While the displacement of runner B is negative because they are running to the left, what we're actually looking for is just the value, the magnitude of it. So here's where I'm going to plug some things in. We said that delta XA was 8 meters per second times time. And that's going to be equal to, I'm going to leave my units off, but the units are there. I'm being a little lazy. Equals 10,000 meters. I guess I should do meters per second, but still. All right. Minus, and here's where the magnitude's important. So we had negative 11t, but since I'm taking the absolute value of the magnitude, I want just the number, which is going to be 11t. Oh, let me do that in blue so that we can see it more clearly. This is runner B, 11t. Great. Okay, well, I could add this back over, which is probably what I should have done in the first place. So I want to solve at this point. The only thing that I can find is t, but that is still useful for me. So I add 11t back over to the other side. Turns out I didn't need to keep it this way. I could have just done delta XA, the magnitude, plus delta XB equals 10,000 meters. There are a couple different ways to solve this, so I apologize if that's been confusing. But we'll add 11t over to the other side, and we end up with 19t equals 10,000 meters. Grab my calculator. Here we go. And then I want t, so I'm going to divide both sides by 19. Technically, this is 19 meters per second. Remember the units, meters per second, meters per second. So 11 plus 8 is 19. 19 meters per second. Our meters are going to cancel out, and we have seconds in the denominator of the denominator, so it flips up into the numerator. So I'm going to take 10, 1, 2, 3, 10,000 divided by 19. And I find that the time it's going to take for these two people to meet up is 526.3. I'm just going to keep it 526 seconds. Great. And now that I have that, I can go back to any of the equations that had that original t in it. We could do delta XA is equal to 8 meters per second times t, and we now know the time it takes for them to meet up. So I take 8 times 526, and that gives me delta XA is equal to 4,208 meters. And delta XA is probably the easier one to work with because that's our displacement from here over to here. So now we know that our position is 4,208 meters. So we go about 4.2 kilometers away from A's starting line, and we set up our camera there, and we relax while we wait for the 526 seconds. That's divided by 60. That's about almost 9 minutes, 8 3/4 minutes. Great. Let's double check something real quick, just to make certain that we haven't made any math errors, which is entirely possible because I'm not going off of notes here. Let's double check our delta XB. We said that there was negative 11 meters per second times our time, which we now know to be about 526 seconds. So if I take 526.3, if you'd like, times negative 11, I end up with my displacement is negative 5,786 meters. So we're saying that this is 4,200 and this is 5,800 roughly. So now remember, this one is negative because they are moving to the left. So I would take that as a positive value, just the magnitude to find my total here. So this plus 4,208, and we end up with 9,994, which is just shy of the 10,000 meters. Why is it not exact? Well, because I did some rounding in there. I used 526 seconds instead of 526.3. So if you keep some additional significant figures on there, you'll probably get it exact, but that's probably not necessarily realistic in that people are probably not going to be running exactly 8 meters per second the entire time. So, all right, this is a more complex kinematics problem, and it's more complex because we have to use technically a set of systems of equations to actually solve it, because we're asking a very complex problem that deals with two people engaged in one-dimensional motion. Now, real quick, I'm not going to have a follow-up video with this, but there are some things that could switch out on this. Okay, sorry about the cut. The video stopped right there at the end, but I wanted to follow up with some other possibilities. So real quick, we've got the problem that we just solved where both people are starting on opposite sides and running towards each other, and they start running at the same time. What are some other ways that I could have asked this question, or ways that it might change? Again, this could be a very real-life scenario where you might have to set up something for a special effects shot where you have two cars speeding towards each other and you want to have the point in between where they're going to meet. And so this is a great place where you could actually work with that, but it might change. So for instance, what are some ways that it might be different? Well, what if I set up that it was a race, but not necessarily a fair one? Let's say that runner A is still going at 8 meters per second, and runner B is still going at 11 meters per second. Although this time I'm going to make it positive, because let's say that they start off kind of neck and neck. I did not intend for the velocity to go with them, but okay, let's say that they both start here at x equals 0. But what if instead, when the starting watch starts, runner A starts going, but what if runner B gets delayed for whatever reason? Maybe runner A started running early, or runner B had their shoe untied and they had to stop and they had to tie it, and that took another, I don't know, maybe 30 seconds. So runner A had a 30-second head start. 30-second head start. Well, you could still do exactly what we did before, except things are going to be a little bit different. If you wanted to catch the point where they're going to catch up to, with runner B catching up to runner A, we'd still need to set up a lot of the same things that we've got. First off, runner B's velocity would be positive 11 meters per second, because this time they're headed that way. The next thing that we could set up is the following. Our times would not be the same. Time A would not be equal to time B, because runner A has been running for 30 seconds longer than runner B. So I can do the following. I can say that TA is equal to TB plus 30 seconds. It's another relationship, and it's a little more complex than the one we saw before, but it works exactly the same as delta XA equals delta XB, well, plus delta XB equals 10,000 meters. It's the same type of setup that we had before. And here, because you still need some additional information or additional things that you could work through, you could also set up that what we're looking for is the point when runner A or runner B catches up to runner A, at which point they must both have gone the same delta x. In this particular problem, the times are different, but delta XA equals delta XB. This is the same type of equations that we had before, although last time they had equal times and there was a relationship between the displacements. Now we have equal displacements and a relationship between the time. I could have also made this even more complex by maybe runner A starts at x equals 10 meters. And runner B starts at x equals 10 meters, but runner A has a 2-minute head start and starting from x equals 0. At which point neither of these would be directly equal. We could then set them up. I recommend drawing these things out and keeping track of them because that's the best way of working with it. But you could deal with all of this. On top of that, you could even have, let's say it's not people anymore. Let's say that it's something like a car instead. You could even have something that has an acceleration. We found that delta x, our displacement, could be described in terms of our initial velocity times our time if your acceleration is equal to 0. But what if instead they're starting from stop, my initial velocity is 0, but I have a constant acceleration, maybe 3 meters per second squared. I could then set all of this up where delta x, our displacement for that car, would be our initial velocity times time plus 1/2 our acceleration times time squared. Well, when I plug in that v naught is 0, then this disappears into a puff of nothingness. And even if I don't have a constant velocity, but I do have a constant acceleration, I could end up with still an equation. That delta x, the displacement of this car, would be 1/2 at squared, and I could use that just the same as we did with the previous one, right here, where we had the velocity times the time. Instead, I could have 1/2 at squared if it's starting from a stop. Or if it's not starting from stop, I just have a longer relationship here. But it doesn't change what we've got. We're describing how far something has moved in terms of something else. In these cases, you can do this with any of them. There's nothing special about your displacement. If you had a relationship between their speeds, their velocities, you could work with that. It all depends on how you can set these up and put them in relation to one another. So this is a great example of a much more complex and harder one-dimensional kinematics problem. Now, the main way to make one-dimensional kinematics difficult is either have two objects or compound motion, where one is doing motion of some kind for part of it and then switches to a different type of motion. And so you have to keep track of it. Remember, your kinematic equations can only be applied during periods where the acceleration is constant. So that acceleration could be 0 or it could be a constant number. But if your acceleration changes, you're going to have to do one section and another section to account for it.